Now for 3.6, generalized inverses. Okay, we'll clean up some of the stuff we had from the previous section as well. Actually, we'll consider generalized inverses and something called a pseudo inverse. Okay, so where we left off in the last section is we've got some properties of generalized inverses. We denoted generalized inverses of given matrix A with it's kind of like a superscript negative sign. And we've seen, for example, that in the system AX equals B, X equals a generalized inverse of A times B is a solution to a system of equations, giving us some inspiration for looking at generalized inverses. But what we haven't done is figured out whether or not they even exist, let alone how to find them. So in this section, we'll look at generalized inverses a little bit more. I mean, our big accomplishment is that we will show that they exist. We'll see in general that they may not be unique. If A is invertible, then all this inverse stuff will collapse down to the kind of thing you do in linear algebra. But if A is not invertible, for example, if it isn't square, then we'll show in particular that generalized inverses exist, and we'll see that they are not unique. We'll also introduce something called a pseudo inverse, also called a Moore-Penrose inverse. We'll show these exist. We'll give sort of a technique for computing them. And these are unique. So these pseudo inverses are unique, whereas the generalized inverses are not. And I need to address some comments made in our textbook. So the following comments apply to the first edition of Gentle's book. The second edition I don't have access to. I'm not sure if they've corrected it or not. There is a second edition out. Came out in I think about 2018. Gentle claims on page 101 that the results of theorem 3.3.17, let's jump to 3.317 was some claims about inverses, just a bunch of claims about inverses. I think we left these as an exercise. Here we're talking about regular inverses, but Gentle claims these results hold as well for generalized inverses, but they don't. There's an errata. Here's a link to the errata for the first edition of the book. States that it should read, these results do not in general hold for generalized inverses. Gentle gives a formula for generalized inverse of a partitioned matrix. Who am I to say, but I'm a little skeptical about the validity of that. Let's analyze this generalized inverse stuff a little more closely. We will now establish the existence of generalized inverses, and we'll show that they're not unique in general. Okay, so a little bit of a problem in this stuff in particular in the Gentle book, but let's clean it up. Okay. For n by m matrix A and m by n matrix, generalized inverse of A satisfies, recall, A times generalized inverse of A times A equals A. If A is invertible, then we could take A inverse, and that would certainly, say, produce an identity matrix in the first two. And that would certainly work for a generalized inverse as well. Hey, if A is a zero vector, that is, if the rank of A equals 0, the only way the rank can be 0 is if there aren't any non-zero entries in the matrix, would imply the column space has dimension 0, so all the columns are 0 if you like. So if A is a 0 matrix, then to get this satisfied, if A is a 0 matrix, on this left-hand side, no matter what we do of appropriate size, m by n, I guess, we could choose anything for this generalized inverse, and you do the product on the left-hand side, you're going to get the 0 matrix back out. So the 0 matrix has a generalized inverse. In fact, every appropriately sized matrix is a generalized inverse of the 0 matrix. So that's pretty weird. That shows right there we don't have uniqueness. Yeah, but we're looking at the zero matrix. We can do a little bit better than that. But that does destroy general uniqueness in general. All right, Gentle makes some comments. These are correct, so we'll check them by computation. It says if we take matrix A to be partitioned into these pieces, as usual, where A11 is a full rank and the same rank as A, then we can find a generalized inverse of A as given here. I agree, because it's an easy computation. All right, now you've seen in the past, and this is how we'll deal with generalized inverses, that we could take matrix A with some permutation matrices and in effect isolate the rank of A in a little identity matrix up here. More of that to follow. But the claim is that a generalized inverse of A, under the hypotheses that we've partitioned it in such a way that in the upper left-hand corner, we've got a full rank matrix, same rank as matrix A, then this is a generalized inverse. So we need to show that this alleged partition matrix, which is generalized inverse, actually satisfies A times this thing times A equals A. So here's the computation, straightforward. Matrix A, we've partitioned above into these four pieces, so we'll get that on the outside. We're alleging this to be a generalized inverse, so we'll put that in the middle. Do your usual multiplication for partition matrices, row times column style. First row, first column will give us an identity matrix of size R by R, if that's the rank of A. But we indeed get an identity matrix here. First row, second column will give us zeros. Second row, first column, get a little more complicated. We'll have A sub 2, 1 times A sub 1, 1 inverse plus 0. So we'll have this entry here. Second row, second column, the zeros will produce a 0 down here. Taking the product of these two, now multiplying that by the other copy of A, row times column stuff again, A1, 1, first row, first column, first row, second column, A1, 2. Second row, first column, the A1, 1 inverse and A1, 1 come together to leave us with an A2, 1 plus a 0 from the remaining entries. And second row, second column will give us an A2, 1, A1, 1 inverse, A1, 2 plus 0. Okay, so that'll produce this. Okay, so we've seen, in fact, when we were doing the Schur decomposition stuff, that in the event that we have a full rank matrix up here, it must be that we had this A22 entry, we had this entry down here, equal to, remember it was this one times the inverse of that one, times that one in that order, A21 times A11 inverse times A12. Section 3.4, the second page of the notes, we had seen something to that effect. So this quantity here, given the rank of this upper left-hand part, this must be A22. And so indeed, this matrix equals matrix A. So there's an example of a generalized inverse of matrix A. Okay. That dealt with A being partitioned in a particular way. To get that to work, A had to have a full rank, little submatrix up here. A might not come to you in that way, but we can get, through permutation matrices, as we've seen in the past, we can get that full rank matrix up in the top. And that's how the proof of theorem 3.6.1 goes. It says, let A be an n by m matrix, then a generalized inverse of A exists. Okay, let's look at the proof of that. All right, first off, if the rank of A is 0, we just saw that there's a generalized inverse of matrix A. It's its own inverse, if you like. every appropriate size matrix is an inverse. So we're claiming existence here. And remember, we've made a comment that these won't be unique. So in the following, let's see where uniqueness falls apart. So zero matrix is processed. Suppose we don't have the zero matrix. That is, suppose we have a matrix A of rank greater than 0. I'm going to jump back and forth between the notes to justify these various claims. By theorem 3.3.9, when the rank of A was positive, there exist matrices P and Q, both products of elementary matrices, such that A equals P, identity matrix, Q with zeros here. The idea was we took A and basically did row and column operations to it to put it in a row echelon form, a particular kind of row echelon form. We're also getting to use some column operations as well. Let's take a peek at that. So let's see, 3.3.9, I got 3.3 in the background here. Let's move back up where we explicitly said that, make sure we're quoting it correctly. There it is, and exactly. A is an n by m matrix of rank greater than 0. Then there's matrices P and Q as described, such that PAQ equals an identity matrix size R by R, where R was the rank of A, and then 0 matrices surrounding it. We did some row reduction to establish that proof-wise. Okay, so we can permute things around and write A in this form. Now, all elementary matrices are invertible. P and Q are products of elementary matrices, so P and Q themselves are also invertible. So we want to consider the following, and here's where the uniqueness is disappearing. We want to consider the matrix Q inverse, this thing, P inverse. This thing has an R by R identity matrix in the upper left-hand corner. U, V, and W are of appropriate sizes to partition a matrix of size n by m. All right, so we're getting, for example, U is R by m minus R, so R rows, right. So the rows match up with this I sub R, and m minus R columns. Okay, so we've got a total of m columns across, similarly for these others. Now, if A is rank R, if A is rank R, how do I want to say it? If R is sufficiently large, then we're getting some of these dimensions to be 0. In particular, if R is rank n and m equals n, if we got a square matrix of full rank, these matrices, they can't be there. They'll have dimensions something by 0, implying that they're not there. So we'll simply have an identity matrix here. So when A is invertible and square, you don't have room for these UVW matrices. When A is not square, or A is not invertible, then square and not invertible, you can put anything you want to here. So that's the plan. So we will have uniqueness when there's not room for these, but when there is room for these, we won't have uniqueness, to put it informally. All right, so we're going to claim that thing there is a generalized inverse of matrix A. So what we need to do is take A and that thing there and A and do the multiplication. All right, we had written A as P times this times Q. So we'll make that substitution for this copy of A and for this copy of A, P times this thing times Q. All right, so we want to show we get A out, and it ain't going to take long to do. By writing A in terms of these P and Q matrices, we get the Q and Q inverse together here, the P inverse and the P together here to become identity matrices and be dropped. So we lose that, and it reduces down to this product of 3 matrices. Let's do our row times column stuff. First row, first column gives us an identity matrix. All the others produce zeros because of the locations of the zeros. So we get an identity matrix here and zeros here, a P out front, a Q at the end, but that's how we wrote A by Theorem 3.3.9. So indeed, this is a generalized inverse, and U, V, and W, if there's room for, they can be anything. Yeah, these zeros that we introduced when we took A and wrote it in a particular way, those zeros effectively made the U, V, and W stuff ultimately vanish. So it could have been anything. So there's where you see that you get the non-uniqueness. When there's room for U, V's, and W's, you get non-uniqueness. To the notes for this section. All right. We see from the proof that there is a unique generalized inverse of n by m matrix if and only if A equals R I sub R Q, should be P I sub R Q, where P and Q are products of elementary matrices. And so the rank of A would have to equal R, the size of this matrix we get inside. In other words, A is row equivalent to an identity matrix. A is invertible, the full rank. So we've got a generalized inverse to be unique if and only if A is invertible. And that's effectively just that argument about having room to stick the U, V, and W matrices in there. So we know that generalized inverses are not unique. You give me a particular matrix, if it ain't square, it has a generalized inverse, and it's got more than one. It's not unique. It's got uncountably infinitely many, in fact. So that settles the issue in terms of the generalized inverse stuff. We now explore a different kind of inverse, which is unique, called a pseudo inverse. Okay, so we're going to require a pseudo inverse to satisfy these four properties. When we go through the proof, we'll appeal to these four properties. So I'll keep this running in the background. The definition is for n by m matrix A, pseudo inverse of A, also called a Moore-Penrose inverse of A, denoted with a superscript of a plus for pseudo inverse, is an m by n matrix. Right, n by m for A, m by n for the pseudo inverse. Pseudo inverse matrix is required to satisfy the following. A pseudo inverse of A times A equals A. Pseudo inverse of A times pseudo inverse of A equals pseudo inverse of A. Pseudo inverse of A times A is symmetric, and A times pseudo inverse of A is symmetric. So we've got these symmetry requirements. We'll do some things with transposes in the proofs, and these properties 3 and 4 will allow us to, in certain cases, ignore transposes because we've got symmetric matrices. And up here, it'll allow us to do some substitutions for A and the pseudo inverse of A in terms of some different products. All right. First, let's look at the zero matrix in connection with this. If A is a zero matrix, then the pseudo inverse of A must be the zero matrix, we're going to claim. Certainly, if A is a zero matrix, we've got zeros everywhere. Zero matrices will come out of the product, and they're symmetric. We'll get equality if A is a zero matrix here. This is maybe a question on this, but if we look at the zero matrix, we've got that condition 2 satisfied. Well, if we've got the zero matrix for A in this slot here, that product's going to be 0. And so the pseudo inverse of the zero matrix must be the zero matrix. So zero matrix has both pseudo inverses and generalized inverses. The generalized inverse of the zero matrix is everything. It's the right dimensions, right number of rows and columns. The pseudo inverse of matrix A is only the zero matrix of the appropriate dimensions. Right? I do have the m by n in this case. So dimensions have to be appropriate in both cases. Here, though, we have the restriction that the zero matrix has a unique inverse. a zero matrix itself of appropriate dimensions. Okay, well, what about non-zero matrices? What about those with rank greater than 0? And the claim is every matrix A with positive rank, call it R, has a pseudo inverse given by, so it gives a formula for it as well. We're going to introduce matrices R and L to be described shortly. R transpose times the inverse of L transpose A R transpose times L transpose. Okay, so this gives an existence of pseudo inverses. We'll argue after that they're unique. So this is how pseudo inverses must be computed. Now these A's, these L's and R's are required to be to determine a full rank factorization of A. This we saw in section 3.4. So let's run back and look at section 3.4. So taking a matrix A and writing it as a product of a matrix L and a matrix R. And both of those matrices are of full row or column rank. That's what it was. Section 3.4, here's the specifics. We started with a matrix A, and we had shown that that matrix A could be written as a particular product like this. It could also be written as a particular product like that. So a couple of sections ago, we did this. And what was going on was here, we've got a matrix of full L is a full column rank, right, full column rank. Here we've got a full column rank matrix as well. And here we've got a full row rank matrix. So we would call this one L and this one R. Could also be these as L and R. Anyhow, we took matrix A and wrote it as a product of L times R, where L is a full column rank matrix and R is a full row rank matrix. So that was processed. Then back to, back to our notes. Here they are. Back to our notes. Okay, so these L and R things exist as required. That was written in terms of some permutation matrices. I mean, we're not doing a bunch of computational stuff. So to actually compute a pseudo inverse, and we won't really touch on that, though we could backtrack to see what produced those L's and R's in those start equations in section 4, and then go through and compute pseudo inverse using the formula. So our claims are pseudo inverses exist. Here's how they're computed. First, secondly, pseudo inverses are unique. Let's